Mécanique du point, pendulum, experimental study of the pendulum using a smartphone as a home lab. The experimental setup is just a hand, a smartphone, and a battery cable. Real-time smartphone data transferred to the connected PC are the theta angle as here defined and the vector acceleration as measured in the iPhone frame in three components AX, AY and AZ. In polar coordinates, this vector acceleration is written classically with two components, one along the u vector and one along the n vector. We then now want to identify these two components with the data given by the smartphone as the smartphone oscillates. So essentially what we see is that AX should be equal to 0 if the iPhone is perpendicular to the plane of oscillation. Beside, AY is directly the component of the acceleration along the u vector, and AZ is directly the component of the a vector along n. But there is always a misalignment, and then in that case the component of the vector acceleration along n is the addition of the component along x and z, and this is what we have here. We should take that into account. With the following experimental setup, there is clearly always a misalignment. A better setup could be built and would make better alignment clearly. But it is also first fun to control it by hand and to show how far we can go using this setup and relying for the advanced technological aspect only on the smartphone. The pendulum trajectory is characterized by four situations. The pendulum can move on the right up, can move on the right down, on the left up, and on the left down. These are the four characteristic situations. They are studied first on the video YouTube that's called iPhone, Pendule, Énergie, Vitesse et Accélération, on the playlist that's called iMecapProf. So you might have a look on that to see all these four characteristic situations as explored using the software iMecapProf. Two examples are here when you have an angle of oscillation that's equal to 0, that in that case the velocity is maximum and the acceleration vector is in fact very small in that case and is only parallel to the u vector. The other extreme situation is to the contrary when theta is equal to theta 0, which is the maximum angle of oscillation, and in that case the velocity is equal to 0 and the acceleration vector is maximum and is parallel to the n vector. That can be seen also either on the YouTube video, the same one, iPhone, Pendule, Énergie, Vitesse et Accélération, or that can be done if you want to complete the analysis of the four configuration by having a look on another video that is in the playlist Prof de Meca, and that is called Pendule, Vecteur et Angle. On this video, all these four characteristic situations together with forces are explored. You can also use the software iMecapProf connected to software and a PC so that you can do it yourself, exactly doing the experiment here described. You need to do that essentially at the moment an iPhone, the application called Sensor Data, a PC with iMecapProf downloaded on it. Now we go to the second experimental work proposed. So when you do experiment using iMecapProf and that you look at the a vector, the acceleration vector, then you rapidly identify the fact that the component of the the acceleration vector along the n vector of the polar coordinates is much larger than the component of the acceleration vector along u. And we might think about it and see why is that so. So that can be seen first as an experimental result if you still look at this video I mentioned before, on if you look at the A vector, the acceleration vector directly using iMecapProf once again. We can do a bit of analysis in order to understand that, and then we start with the regime of small oscillation so that we can describe theta easily. So we have a description of theta dot, that is the derivative of theta versus time, and the maximum value is then omega theta 0. In case of the acceleration, the angular acceleration, then the second derivative versus time leads to a maximum value for this theta 2 dots equal to omega square theta 0. And we know that AU is equal to minus r theta dot square, and AN equal r theta double dot. That is respectively, theta dot is the first derivative of angle versus time, and theta double dot is the second derivative of the angle versus time. So if we say that theta 0, the maximum angle, is equal to 10 degrees, that is 1/6 radian roughly, then in that case we see that the component of the acceleration along u at maximum divided by the component of the acceleration along n at maximum, not in the same situation for both, but still, then we see that this ratio is essentially equal to theta 0, which is 1/6, and it shows that essentially the component of the acceleration vector along u must be observed very small compared to an, the component of the acceleration vector along the n vector. Now we can turn to the analysis of the measured data, and we start with the angle of oscillation during oscillation. And for that, we're using essentially the data coming from the iPhone gyroscope. So first of all, we have a look at the expected behavior of theta if the smartphone is freely oscillating. And we should have such a evolution, such a change of the theta angle. And if that is experimentally observed, then it means that we have essentially defined a maximum angle, frequency of oscillation, and the time of relaxation. These are the quantity that we should be able to measure if that behavior is observed, and this is where we're heading now. So what we observed is the theta versus time measured 100 times a second for a period of time that is about 100 seconds, is more than a minute, and an angle moving from 0.3 to 0.05 roughly, which means an angle moving from 15 degrees down to 3 degrees. When the angle is 50 degrees, it's questionable if the approximation of small angle is still valid. But if we do a calculation immediately, we see that the sine of 0.3 is equal to 0.29. So we believe that the small angle approximation is still okay, really. Just looking at the behavior, we immediately observe, at least for the long time, that we have oscillation omega with a frequency omega that is pretty well defined, and that also we observe the relaxation that we expect to describe with the time tau, using theta to t equal t to 0 sine omega t exponential minus t over tau. Let's have a look if that makes sense and if we can define omega and tau quantitatively. So now on this curve we have both the blue curve that we had before, that are the experimental data, and now we have a red curve that's the best fit with omega equal 3.19 plus minus 0.01 radian per second, and tau essentially equal to 35 seconds. If we change omega by 0.01, then we see that the fit is clearly worse. So we have a period of time that's about 1.97 seconds at best, and let's give a length of the pendulum that's about 0.96, 0.97 meter, which makes sense with when you look at the cable of the iPhone we have used. So it's rather amazing to see how well that can be described. Experimental work 4 and 5 are now the analysis of the acceleration data provided by the accelerometer. So as experimental work 4, then we're going to analyze AZ and AX, and as experimental work 5, we're going to analyze AY. Both the set of data are directly provided by the accelerometer. So move to experimental 4. So that's the analysis of AZ along the K vector that's perpendicular to the plane of the iPhone indeed. And what we would like to see if that AZ behaves like theta double dot, that is the second derivative of the angle versus time. And this is essentially looking at the application of the Newton law, that is theta dot equal minus omega to the square theta. So we know theta. Through AZ, we know theta double dot, so we can check if this differential equation is really fulfilled, since we have independently the theta angle from the gyroscope, and we have the theta double dot from the accelerometer when we measure AZ. R, we know it because we measured it before, it's 0.96 meter. So let's have a look on that, and first we go to the bare data after summarizing. What we want to do now is to compare AZ with R omega to the square theta. So first of all, the measured data directly. So once again we observe the clear and well-defined oscillating behavior, which is no surprise since this is what we have prepared with the iPhone. And as we stopped exciting the iPhone displacement and keeping the end still, then we see that we clearly observed again relaxation. Now the point is, can we directly calculate this curve by using the theta analysis we've done before? And this is the slide now coming. So the comparison of AZ and minus R omega to the square theta is here. And it's rather amazing to see that at this scale we cannot distinguish by eyes very easily the difference between AZ and minus R omega to the square theta. The agreement is something like 5% for most of the point. We have to say that here we've taken into account AX and the misalignment for this data analysis, but this is not in fact a key point at the end. It's interesting to go further in time, and the previous set of data presented were between 90 seconds and 150 seconds. If we go further in time and we have a look on the agreements between the theta measurement and the component of the acceleration AZ in time, when we are in the period of time between 150 seconds and 180 seconds, then we see that the discrepancies is much more obvious. And this error increases with time. This is what we observed here. But nevertheless, it means that we definitely show how good is the differential equation experimentally here verified. Experimental work 5 now is looking at the analysis of IY that is connected to minus R, theta dot to the square. Theta dot once again is the angular derivative versus time. We know AY from the direct measurement provided by the accelerometer, and we know theta dots that from the measurement of theta, in fact. So the bare data here are, this is the measured AYT with the accelerometer, And this is essentially what we expect. Since AY is related to the square of the first derivative of the angle theta versus time, then we expect a doubling of the frequency. And this is what we definitely observe here. We also expect that all the data will be on the same side of the zero axis. That is true, nearly true, and this is a problem we have here before doing any fitting or better analysis. What we observed on the Bayer data is that we have a kind of an asymmetry, and we have part of the AY data that are on the positive side here, and they should be all on the negative side. The reason why this is so, we don't quite know, but this is the way it is. So if you have any idea about that, it's welcome to tell us. So if we do now the theoretical analysis, then we start with the best fit we had for theta, and then we know theta naught, we know omega, and we know tau. All these values are well defined now. So we do the calculation, and then we have a complete expression for theta dot to the square. And that now we can compare directly without any adjustable parameter where we are now. They all be defined by the analysis of theta, and we can just put the two curves together and see what's happening. And this is what we have. The blue curve is the AY measured. The red curve is the calculated minus R theta dot to the square. Well, we have a very good agreement in the sense that the scale are essentially the same. Omega used really reproduce the oscillation of the AY, and theta and the relaxation time tau used is clearly correct. We observed, as we mentioned previously, that we cannot explain why there are positive value for AY, and again, let us know if you have an idea about that. So we come now to the conclusion, and first one would be if you're interested and if you think this is of worthwhile to do this kind of experiment, and try to do better, and let us know how to do it, and we would be very pleased to see it. So we propose here that the smartphone is essentially a home lab for physics and for students. This enables them to do key experimental works at home. With then pendulum, we also then rotation, and with then oscillation of mass and spring system. You can do displacement with vector velocity constant or acceleration vector constant that can be done essentially freefall. Other things based on the technology of smartphone can be done in optics, acoustics, and other fields, and this is an open possibilities. Thank you.